you to the organizers for hosting such an excellent conference. And in this talk, I will present a novel approach to code-based cryptography that addresses the limitation of the classic McEliece system, while at the same time achieving significantly stronger security by factors well beyond 2 to the power of 100. The method builds of what I refer to as high memory masked convolutional codes. My name is Meir Ariel, and I'm the head of the Space Engineering Center at Tel Aviv University. My interest in this topic first arose while building a satellite for QKD, for distributing quantum encryption keys from space. However, during this effort, I realized that if we could design an algebraic scheme that resists quantum attacks as targeted by the NIST competition, then we could achieve the same security using only software running on a mobile phone. So in that case, the enormous effort of building QKD satellites and optical ground stations to detect the quantum keys might become unnecessary, or at least it will never become a commodity. So let me begin with a short introduction. Code-based cryptography relies on the hardness of decoding random linear codes. It was first introduced by Robert McEliece in 1978, who employed a binary GOPA code to build a public key encryption scheme. It has a long history of resisting attacks and thus became a candidate for PQC. Now, the core concept, I hope this is not interrupting with the title. The core concept disguises the generator matrix of a GOPA code using invertible linear transformation, resulting in a disguised matrix, G prime. Now, if M is the plaintext, then C is the code word generated by multiplying M by the disguised generator matrix. The sender then deliberately introduces errors into the code word, so the ciphertext is given by C plus the error vector, making decryption challenging for attackers while allowing the recipient who possesses the private key to correct the errors and retrieve the plaintext. Now, despite it, let me just maybe move this. Despite its solid theoretical foundation, classic McEliece suffers from practical limitations, most notably its reliance on fixed GOPA codes with rigid error correction capability, essentially limited to parameters such as n, k, t equals 1024, k equals 524, t equals 50, where n is the length of the ciphertext, k is the length of the plaintext, and t is the maximum number of errors that can be reliably corrected by the code. In other words, k by n are the dimensions of the generator matrix. Another example is the following: n equals 4096, k equals 3556, and t equals 45. But this is just another example. There are not too many possibilities. Another limitation is that the decoder is an algebraic error correction decoder. And this means actually that it is not very suitable for hardware implementation. And most importantly, the performance is not very good for small t, and t is usually small because GOPA codes are not powerful codes. Okay, so what happened was that The classic McEliece advanced to round 4 of the NIST PQC standardization process, but was not ultimately selected for final adoption. Our work introduces a novel PQC approach based on several advantages over traditional code-based crypto systems. The first advantage is diverse code selection. A wide range of convolutional codes can form public and private keys, allowing customization to meet specific security needs. Secondly, much stronger public key security. Our method, high-density generator matrix with a random-like structure, significantly improves security against cryptanalysis compared to low-density matrices or other code-based systems. The flexibility to select a convolutional code with super strong error-correcting capabilities enables the introduction of a much higher number of random errors, hundreds instead of dozens, boosting cryptanalysis resistance by factor exceeding 2 to the power of 200 compared to classic McEliece. Scalable key length and decoding complexity. Unlike block codes with fixed dimensions, our scheme supports plaintexts of arbitrary length, and the recipient's decoding complexity scales linearly with the key length. And finally, software hardware implementation. The decoder process actually uses an array of Viterbi decoders based on directed graph methods, facilitating efficient hardware and software implementations. Now, what is a convolutional code? For those who are not familiar, a convolutional code is defined by a set of n polynomials, each of memory up to p. Customarily, those polynomials can be structured into the form of a polynomial generator matrix, but this is just a notation, not more than this. Okay, now here is an example of how the decoder looks like. The input, which is the information sequence, is shifted through a shift register with some exclusive OR operations between its cells. Now, in fact, each output can also be described in polynomial form as the product between the polynomial input and the polynomials describing the encoder. In this example, the encoding operation is indeed represented by these two polynomials, p sub 0 and p sub 1. In this case, we have one input and two outputs. So actually, the output of the encoder is obtained by interleaving the two sequences. But we can use stronger codes with more than two outputs. The parameter p, in our example p equals 8, determines the number of states 2 to the power of p in the trellis diagram. What is a trellis? A trellis is a directed graph representing the code structure, and thus p influences the complexity of decoding using the Viterbi algorithm. So in our example, this is a graph, a quite complex graph representing the convolutional code with 256 states in the trellis. The same trellis serves for decoding the convolutional code. Here is another example with p equals just 2, just to show you more clearly how a trellis looks like. In practice, p is rather small to limit the complexity of the decoder, usually up to 14. Still, 14 means a 16,000 state trellis and a very powerful code. The encoder, luckily, has a scalar representation that is very similar to a generator matrix of a block code, but with infinite dimensions, where the GIs, those bold GIs, are the matrices of the coefficients of the monomials of the polynomials. Now, a convolutional code can be very powerful, but we can see immediately why it is problematic using such a code. by just looking at the matrix GP. It is quite difficult to disguise the matrix because, first of all, it has very low density, mostly zeros, assuming that there are 10,000 columns, for instance, and not too many ones. Also, each row is just a shifted version of the previous row. So, for example, if we apply column permutation, the original positions of the columns are still recognizable, but simply counting how many zeros are there below the last GI in each column. So this is why these codes were never used. Now, what we do is to each polynomial P, we associate a high memory polynomial Q with degree up to Q. And small q could be hundreds. Now, the proposed algorithm imposes no restriction on the choice of the high memory polynomials. However, in practice, P is rather small to limit the complexity of the decoder, usually up to 14, while Q is usually larger than 200. In principle, a Viterbi decoder can be used for maximum likelihood hard decision decoding of the code based on the product of the two polynomials. However, this approach becomes impractical for large values such as 2 to the power of 200 or 300. Too many states. Now, to scramble the high memory polynomial matrix, DPQ, this is now a high memory matrix. Disrupting its diagonal structure, we add to each row a random vector selected from a predetermined set, predefined set of random vectors. So what we do, we actually apply masking to the code. So in other words, this is a masking by a k by n masking matrix G tilde of rank L. So the masked generator matrix is then constructed as the sum GPQ plus G tilde. The resulting matrix is now fully dense, having completely lost its diagonal structure. Also, since GPQ had originally full rank, the sum GPQ plus G tilde can be chosen to have full rank as well, and is therefore well suited for subsequent invertible transformations. So we made a complete mess of the original matrix. Now, the final encryption matrix, which serves as the public key, is obtained by applying both row and column permutation or transformations. S is a random K by K binary matrix used to hide the encoding, that is the correspondence between the plaintext and the ciphertext. And R is an n by n random permutation matrix. And we refer to the code described by G as a high memory masked convolutional codes. Now, the transformation that we did from GP to GPQ and to G involves several steps. Some are reversible and some others are semi-reversible, but ultimately producing a fully dense random-like matrix structure. And this structure offers much stronger resistance to cryptanalysis compared to low-density matrices or those with recognizable patterns. Now, to finalize the construction, we add an error detection mechanism such as a CRC, and this encoding steps applied to the plaintext enables the recipient to detect decoding failure because the Viterbi decoder might fail. Unlike block codes, convolutional codes do not guarantee successful decoding, even when the error rate is within correctable bounds. Now, what we do now, we add errors. Let E denote the actually the probability that the sender flips a ciphertext bit. This parameter E is selected by the public key owner and is chosen to be sufficiently large to enhance resistance against attacks. And now we are ready to define the public key as GER, R is the CRC, and the private key as all the other transformations. Now, notably, due to polynomial division at the decoder, because we must reverse the multiplication by the high memory polynomials, the effective error weight may increase further. More noise is injected during polynomial division. Okay, now why it is very difficult for an eavesdropper or an attacker to find the original low-density matrix. An eavesdropper observes the public key and the intercepted ciphertext. However, since the ciphertext includes injected errors, inverting G directly is useless for recovering the plaintexts. Additionally, attempting to invert the multiplication by the high memory polynomials in the presence of noise triggers more noise, triggers error propagation. More noise is injected during decoding. When you have the product of two polynomials and you divide the product by one of the factors, you get the other factor. However, if the product contains errors, the division by one factor does not yield the other factor, but the other factor with a lot of errors. So you may start with a 2% error rate and end up with a 7% error rate due to polynomial division, or even 50% error rate, depending on the polynomials that you choose. So the attacker's options are limited to either checking all possible error patterns, this is an operation exponential in the error weight, or attempting to recover the original matrix from the public key. The second approach is defeated by the scrambling applied to the full-rank high-density random-like matrix. Now, for an adversary, G tilde is completely unknown. He doesn't know what matrix was used for masking. Although its rank is small, the space of possible masks is enormous. Exhaustive search over this space is infeasible in practice, and ciphertext errors prevent efficient verification of any guess. In conclusion, the obfuscation erases visible patterns and makes the columns of G statistically indistinguishable from those of a uniformly random block code. The only known generic decoding method is information set decoding, ISD, with complexity exponential in the error weight. But how the recipient gets over this mess? At the decoder, we first apply the inverse permutation. Since E is a random error vector with an unknown Hamming weight, its permutation is simply another random error vector with the same weight, so we don't care. The effect now of the masking G tilde must be reversed. However, this masking is not entirely reversible. While the recipient has full knowledge of the masking matrix because he invented the masking matrix, the plaintext remains unknown. Consequently, the specific linear combination of the rows of G tilde, the masking matrix, that was added to the ciphertext cannot be uniquely recovered. To reverse the masking, we need to consider all masking possibility. But for us, this is just a polynomial difficulty, not exponential. Any such candidate masking is determined by deinterleaving the masking to its constituent polynomial products. Then each product is divided by the corresponding high memory polynomial, and at this stage of decryption, the recipient cannot determine which quotient is the correct one. The quotients are then re-interleaved to form a code word plus errors in all possible combinations. But in the general case, there are not more than 2 to the power of L candidates. I have about 4 slides left only. We now aim to determine the most likely plaintext by applying Viterbi decoders to all possible candidates. And this decoding can be performed in parallel for improved efficiency. Now, the most likely code word is the one that minimizes the weight of the error vector, and then we can calculate the CRC, and if it checks, we reverse the plaintext by discarding the CRC bits. Now, why decryption should be successful by us, by Bob? Because the numbers of errors corrected, including those caused by error propagation, can be uniquely or quite accurately estimated based on the value of the error rate E and the knowledge of the high memory polynomials. For all the candidates but the correct one, Viterbi decoding of a random vector effectively returns a random Cossack leader. This is the error vector that produces the nearest code word in Hamming distance. Why random Cossack leader? Because the decoder will certainly fail due to the 50% error rate in the unknown candidates. So the decoder will wrongly choose the closest code word. The expected weight of a random Cossack leader can be approximated using the Gilbert bound. So we will be able to distinguish the correct plaintext simply by counting how many errors were corrected. That's it. Okay, to compare the complexity of high memory masked convolutional codes with other code-based methods, we adopt the measure described in a paper by Daniel Bernstein. This is the complexity measure for ISD. And for a quantum computer, we just take the square root of the previous expression based on Grover's algorithm. But this time, each operation is a quantum operation, or quantum iteration involving qubit operations. We now calculate the complexity of ISD of the GOPA code, and we get approximately 7 times 10 to the power of 40 operations. For a high memory mass convolutional codes with the same key length, we get a much higher number, 8 times 10 to the power of 102 operations. For this, to achieve this security, we chose polynomials of degree 14, Q of degree 386, and an error rate of 2%. But 2% yielded 7% at the input to the Viterbi decoder, because additional noise was introduced by polynomial division. And so what happened is that the correct candidate actually was found within a distance of only 400 errors from the ciphertext, but the incorrect one were found at a distance of maybe 600 to 700 errors. So incorrectly unmasked candidates are decoded to code words lying at a greater Hamming distance, and the valid plaintext can be identified with overwhelming probability, while incorrect candidates are systematically rejected. And under this assumption, as I said, the security of the high memory mass convolutional codes is approximately 8 times 10 to the power of 102, and this reflects a security improvement by a factor of more than 2 to the power of 200 compared to classic McEliece, and for quantum decoding, more than 2 to the power of 100. Okay, with regard to complexity of array of Viterbi decoders, we just count the total number of add, compare, select modules for plaintext bit, and this is 2 to the power of L plus P. In our case, 2 to the power of 19 for a convolutional code with memory 14 and L equals 5. And this means about 0.5 mega add, compare, select operations per input bit. This code was originally invented by NASA for deep space exploration, but today it is a computational load well within the capabilities of commercial processors, including those found in modern mobile devices. And this is my last slide, conclusion. This work introduces a novel PQC scheme based on high memory mass convolutional codes, overcoming key limitation of traditional code-based approaches. The interplay of semi-invertible masking, polynomial division, and invertible scrambling ensures that decryption without the private key remains computationally infeasible, and the scheme achieves performance improvements over classic McEliece by factors exceeding 2 to the power of 100 against quantum adversaries, and 2 to the power of 200 against classical adversaries. So beyond its strong security, the scheme supports arbitrary plaintext length, scales efficiently, and enables high throughput via parallel Viterbi decoder, and this property makes the proposed construction a compelling candidate for both classical and quantum deployments. So I'll stop here. Thank you very much for your attention.